Okay, thanks, Rhonda. Again, welcome to the series, and today we will focus on the air interface aspects, specifically OFDM, OFDMA, and SC-FDMA. So basically, in a 3G system, we are relying upon CDMA as the multiple access technique, and in 4G systems such as LTE, we are moving toward OFDMA technology. Okay, so that's the major shift in terms of the multiple access technique. Okay. In case you have not yet seen, this is my picture that will help you relate the voice to my picture. Okay. Before we get started, a couple of questions for you. If you could please pick your selection here and let me know what kind of work you are currently doing. I will give you about 30 seconds to finish this up. And please participate in all the polls. Okay, that's a very, very important way for us to get feedback. And we would request you to submit as many questions as possible. And to do that, we have two basic approaches. One is you can type in your question in the questions box, and we will periodically open up the bridge. Okay, so when we unmute the bridge, you can ask questions using the bridge. Okay, so these are two basic ways. But the more the questions, the better. Okay, it will help not only yourself, but also your colleagues. So please maximize the use of the questions box. Okay, so this is what you are indicating, about 50% customer support, 20% system test integration. Okay. Very good. Okay, thank you. Another question. What kind of details do you want for this session? And your answer to this question will help me figure out the type of details I should provide. Okay. So please take a moment or two to provide me this feedback. Uh, 10 more seconds. Okay. So, about 65, okay, about 70% want few details, and the remaining 30% want a lot of details. Okay, so I would try to keep it at the medium level of details. However, if you want more details, the best way to get your information is to ask questions. Okay, we want to make sure that everyone gets whatever that person desires from this session. Okay, so please make sure that you submit your questions. Okay, in case you want additional information. Okay, just one more question, and then we will start the session coverage. Your answer here will help me decide how I should relate the concepts, okay, of LTE to what you may already know. Okay. And again, thanks for participating all these polls, and continue the use of the questions box. So some of you used that in the last session, so please continue doing that. Okay, about 65% with 1X and DO background. Okay, and the remaining, okay, will also have exposure to other technologies. Okay, thank you. Thank you for your participation here. The next few pages we have acronyms, so feel free to refer to that. And we also have an integrated list for the entire series. So it would be good for you to keep a copy of that. Okay. Okay. And of course, you can always ask me a question about the acronym. What do we plan to accomplish today? This is what we have. The basics of OFDM, orthogonal frequency division multiplexing, OFDM. The OFDM signals are relatively complex. So if you want to understand the signal, you need to look at various perspectives. So we will look at both the time domain perspective and frequency domain perspective of the OFDM signal. OFDM signals face certain challenges from the radio environment. For example, multipath. To help us solve the multipath problem, OFDM systems utilize so-called cyclic prefix. When the users are moving around, the OFDM systems face another challenge, and that challenge basically is related to the Doppler shift. And to take care of the interference caused by the user movement, we need to have adequate spacing between the radio channels in OFDM system. So we'll consider both of these topics, okay, as a solutions to those problems. In general, OFDMA systems suffer from high peak to average power ratio. High peak to average power ratio. So on average, maybe we are using little bit of power, but suddenly sometimes we may have a need to transmit more power. So now the difference between the peak power and the average power could be quite high. So how do we take care of that problem? So we will address that problem also in the session today. We'll take a look at how the OFDMA transmitter looks like, how the receiver works in OFDMA system. LTE system utilizes traditional scalable OFDMA, orthogonal frequency division multiple access, in the downlink. So OFDMA is used in the downlink. In the uplink, we use a variation of OFDMA, and that is called SC-FDMA. So we will see the difference between the two. So that's what we have on our plate today. And we will start with the basics of OFDM. As I said earlier, no limit on the number of questions that you can ask. So please ask questions. Okay. Tomorrow morning, when you take shower, think OFDM. Oh, this instructor is saying we have nothing else to do. Okay. During shower, well, what happens when you take shower? The water is coming from this pipe, and the shower head distributes that water into tiny streams of water, many such streams. Each tiny stream carries little bit of water. What is the end result? Nice user experience. If water is warm, if the water is cold, all bets are off. But that is the basic idea. In an OFDM system, large amount of data is sent using hundreds of radio channels. So in this example, we have channel 1, channel 2, all the way up to 100 channels. Each channel carries little bit of data. So let's say 100 kilobits per second. So 100 kilobits per second, if we have only one channel. If we have allocated a user 100 such channels, then you will see that you have very high data. So in this case, 10 megabits per second. In LTE, we can have as high as 300 megabits per second data. So one way to get this kind of very high data rate is parallel transmission on hundreds of these kind of channels. Each channel formally is called subcarrier. So in summary, the OFDMA systems achieve high data rates by parallel transmission of data on many channels, many subcarriers, okay, at the same time. So if I have some spectrum, let's say I have 20 megahertz spectrum, then I would divide the spectrum into many hundreds of subcarriers. Okay, and each subcarrier will carry some data. That's the basic idea. So it means that we have multiple carriers, multiple subcarriers. So let's contrast a traditional multi-carrier system with OFDMA type multi-carrier system. In a traditional multi-carrier system, what we would do is divide the available spectrum bandwidth into several channels, several carriers. So let's say F1, F2, and so on, 6. So we have 6 carriers. In a traditional multi-carrier system, we have some sort of guard band between adjacent carriers. Between two neighboring carriers, we have some sort of guard band. So my question to you is, why do we have a guard band? What is the benefit of having this type of guard band in a traditional multi-carrier system? You can give me your answer by typing in your answer in the questions box. So my question is, why do we have guard band between two neighboring carrier frequencies in a traditional multi-carrier system? What do we gain? Avoid interference. Very good. Thanks, Ryan, for the answer. Okay, the basic idea behind the guard band is to minimize interference. Thank you for your answers. Minimize, and more specifically, inter-carrier interference between two carriers. Inter-carrier interference. Okay, I see. As long as you have enough guard band, then you will be okay. You have minimized the interference and no problem. Okay. So that's what we do in a traditional multi-carrier system. Now, let's contrast that with the OFDM based system. In OFDM system, we take this subcarrier, put it here, another subcarrier. Here now you will see that there is significant overlap between the neighboring carrier frequencies. So now we would be worried that, oh, since we have significant overlap, there would be too much interference. But guess what? How much interference in OFDM? Zero interference. So even when we have significant overlap between adjacent subcarriers, there is absolutely no interference between the two subcarriers because the subcarriers are orthogonal. Just like orthogonal Walsh codes in 1X system, orthogonal OVSF codes in UMPS systems do not have interference among them. Just like that, orthogonal subcarriers in OFDM systems do not have interference among them. And what is the benefit of that? Well, if we do not have to worry about interference among the subcarriers, we can squeeze in many subcarriers in the available bandwidth, and then we can say, okay, I have how many subcarriers now? So let's see how many I could draw here. 14. So if earlier I had 6 and one could carry 1 megabit per second, now in a traditional system I could have supported 6 megabits per second. Since OFDM systems do not have to worry about interference between adjacent carriers, then I could squeeze in many subcarriers here, 14. Each carries, let's say, again 1 megabit per second. This helps me get 14 megabits per second. So rather than supporting 6 megabits per second in a traditional multi-carrier system, I am able to now support 14 megabits per second in case of OFDM system. So that is the beauty of OFDM, that we are able to increase the data rate by squeezing in many subcarriers within the available bandwidth. And the main reason we are able to do that is there is no interference among the subcarriers. They are all orthogonal to one another. Okay? So that's the basic idea. Now, how do we construct orthogonal subcarriers? Okay, now let's take a simple example. I have some bandwidth, maybe 10 megahertz, and then I will divide into several subcarriers. So I have one subcarrier F1, another F2, yet another F3, and so on. So let's look at the first subcarrier F1. Okay. And goal is to construct orthogonal subcarriers. Let's pick some time period, 66 microseconds. That is the modulation symbol period. Modulation symbol period. Let me ask you a very simple question. In simple terms, what is a modulation symbol? What is a modulation symbol? And you can type in your answer in the questions box. And in this example, we have 66 microseconds as the modulation symbol, and that is the modulation symbol period for LTE. Okay, bit. Okay, very good. So one answer that I got, that a modulation symbol basically represents some bit. Okay, very good. So let's take an example. Let's say that I have so-called BPSK modulation, binary phase shift keying, BPSK. So in that case, if I have some modulation symbol period here, 66 microseconds, and if I'm sending a BPSK modulation symbol, this would represent, let's say, bit 1. On the other hand, if I send a signal with another kind of structure, this is a sine wave here, this is a negative sine wave here. So I'm changing the structure of the transmitted signal. So this is another modulation symbol, so maybe it represents bit 0. So when the base station sends out a signal to the user that looks like this then the UE knows that oh, this corresponds to bit 0. It means the base station wants to send me bit 0. After some time, when we get a signal that looks like this, then the UE knows that oh, this looks like this kind of modulation symbol. It means base station wants to send me bit 1. So basically, the modulation symbol is nothing but a representation of bits, and we do that in the form of some sine wave and cosine wave. So another answer that I got is a group of bits. So right, so one or more bits, right? A group of bits. Either there could be one bit or there could be multiple. BPSK, one modulation symbol, represents just one bit. If you have QPSK, then it will represent 2 bits. Right? 16 QAM represents 4 bits. Every modulation symbol, maybe this sine wave represents now 0, 0, 0, 0. 64 QAM, that is the highest order modulation in LT. In DO, 1xc DO, this is the highest order modulation that we support. Okay, 16 QAM, but in LT we are moving to even higher order modulation, 64 QAM. 164 QAM modulation represents 6 bits. So one sine wave will now represent 6 bits, maybe 0, 0, 1, 1, 1, 0, something like that. Okay, so now we know about this modulation symbol. Basically, it represents a set of bits in the form of some sort of sine cosine wave. Okay, so we pick some time period for our modulation symbol period, and during that modulation symbol period, this modulation symbol is representing one or more bits. That is the idea. Okay, very good. Now, let's construct another subcarrier F2. Number 2, we will have 2 full cycles of the sine wave. One cycle here, another cycle here. Let's construct the subcarrier number 3, F3. Now 3, we have 3 full cycles of the sine wave, 1, 2, and 3. Now if you have full cycles, integer multiples of cycles of the sine wave within the modulation symbol period, then you have constructed orthogonal subcarriers, and there is no interference between 1 and 2, between 1 and 3, between 2 and 3, etc. These are all orthogonal to one another. That is that. Now, what is the frequency of this subcarrier? So you have one cycle here, so the frequency will be 1 divided by T. So 1 divided by 66 microseconds, 66.6 to be exact. That will give you 15 kilohertz. F2, you have 2 cycles, so the frequency doubles. So it is 2 times F1, 30 kilohertz. F3, 3 times the carrier frequency of F1. So 3 times 15, 45 kilohertz. So basically, the spacing between 2 subcarrier spacing is 15 kilohertz. In LTE, fixed, rock solid fixed, cannot change it. Not 13, not 14, exactly 15, because the modulation symbol period is always fixed to be 66 microseconds, and 1 divided by that, you will get the spacing 15. So in summary, we have 66.6 microseconds as the modulation symbol period, and 1 divided by that number, 15 kilohertz is the subcarrier spacing. And the byproduct of such information is that if I have, let's say, narrow spectrum, maybe I have okay, let me pick some number, let's say 5 mega spectrum, or I may have 10. Some reach operator may have 20 megahertz spectrum. So this is all frequency. If I have 20 megahertz spectrum, I would have 1200 subcarriers, and the spacing is always 15 kilohertz. The subcarrier spacing 1 divided by modulation symbol period. Modulation symbol period. And you may be aware of that, but just in case, if you want to see the full view, use F5. Then you will be in the full screen mode. Then you can see the entire drawing that I'm trying to construct here. Okay. On the other hand, if I have 10 megahertz, half the spectrum, you have half the number of subcarriers. So now you will have only 600 subcarriers. Instead of 1200, now it is half, because the spectrum is the half. Then if you go even further, right, then of course you will have 300 subcarriers. That is the basic idea. So the subcarrier spacing is always fixed in LTE to be 15 kilohertz. It means that if you have larger spectrum bandwidth, you have more subcarriers. If you have narrow bandwidth, you have fewer subcarriers. This type of OFDMA system is called scalable OFDMA system. You are scaling the number of subcarriers based on the available bandwidth. Narrower spectrum bandwidth, fewer subcarriers, and wider spectrum bandwidth means more subcarriers. That is the basic idea. It's called scalable OFDMA. And that's the kind of OFDMA we use in LTE and WiMAX both. And in WiMAX, the spacing between two subcarriers is 10.94 rather than 15 kilohertz in LTE. Okay, so let's get back to our slide. Now we know how to construct orthogonal subcarriers. Basically, within the modulation symbol, we should have integer multiples of cycles. Oh, why we chose 66 microsecond? Very good question. Very good. Actually, that is a balance. It's sort of a trade-off. Let's do this. Let's wait for some time. And then we will answer that question. The reason for that is there are certain concepts that we need to be aware of, right, before we can answer that question. So just wait, okay, and we will answer that. But very, very good question. Very good question. Okay. Very good. So we know how to construct orthogonal subcarriers now. I mentioned that OFDMA signals are complex, so we need to look at that from different perspectives. So what you see here is the frequency domain perspective. Frequency domain. So the x-axis here is the frequency, and the y-axis is the amplitude, and we can do power also. That will be amplitude square. That will be power. Okay. The spacing between two subcarriers, F1 here, F2 here, 1 divided by time period modulation symbol period, and we already know 66 microseconds, so that would be now 15 kilohertz for LTE. Oh. So if this guy is at 15 kilohertz, the other would be 30, this would be 45 kilohertz. Spacing is always 15. Okay. Let's say that our E node B has given one user F1 and another user, another subcarrier F2. Just a simple example. Okay. Now, let's say that we are user number 1. Okay. To get our information, we focus on F1. Okay. So this is F1, our carrier frequency, our subcarrier F1. So we are looking at that, and when we look at our center frequency 15 kilohertz, then we will see quite strong signal power. This is the signal power. Signal power on F1. Okay, very good. Let's see how much interference we get from another subcarrier F2. Okay, so we are looking at the center. We are looking at our F1, F2. So the signal amplitude of F2 going down, going down, going down. It crosses the 0 amplitude level when it reaches F1. So it means we have 0 power coming from F2, meaning 0 interference. So we did not get any interference from F2. How about F3? Let's check that also. Going down, and again, whenever it reaches F1, it will again cross the 0 power. So it means no interference coming from F3 as well. In summary, whenever we look at our own subcarrier, then that subcarrier will have very, very high signal power. That's F2. Every other subcarrier will cross 0 power at that time, and it means we have no interference coming from that subcarrier. So that's the frequency domain view. So if you have spectrum analyzer, then you will see peaks of signal power at F1, F2, F3, etc. Okay. Let's look at the time domain view of the OFDM signal. We have symbol that is 66 microsecond long, modulation symbol. We are showing you here 1, 2, 3, 4, 5, 6 subcarriers, F1 through F6. Okay, so F1 will have one sine wave, right? One full cycle on F1. F2 will have 2 full cycles of the sine wave, and so on. F6 will have 6 cycles of the sine wave during the same time period, 66 microseconds. Now we need to be aware of some very simple rules. Okay. So I will just write those in the journal file so that you have a copy of that. You don't need to work. I will do all the hard work. Okay. So during the modulation symbol period, one subcarrier carries one modulation symbol. Very simple. As simple as that. It's very simple rule. Okay. In our example, we have 6 subcarriers. So F1 carries one modulation symbol 1. F2, it has 2 cycles, and those 2 cycles together again represent another modulation symbol number 2. So in this case, we are able to send 6 modulation symbols because we are using 6 subcarriers. So at the same time, we are getting 6 modulation symbols. So from base station to the UE, 6 modulation symbols in a single shot because we have 6 subcarriers. Let's calculate the data rate for this very simple example, and that will start giving us an idea on how these OFDM systems are able to get very, very high data rate. Okay. So we have tiny time period, 66 microseconds, right? And we have 6 subcarriers, and 6 subcarriers means 6 modulation symbols. Let's calculate the data rate. Bits per second. As simple as that. We are sending out 6 modulation symbols. Now, let's use 64 modulation symbol because that is the highest order supported in LTE. Let's see if you remember how many bits per symbol for 64 QAM. Do you remember? 6. Very good. Someone is very fast. Oh, I got a lot of answers. Very good, very good. Thank you for your answers. 6 bits we have. Okay. So 6 bits for modulation symbol. Excellent. And we are sending that in 66 microseconds. Okay. Okay. So we have basically 36 divided by 66 megabits per second. Okay. So let me just simplify. Okay. So let's say about half megabits. Okay. So if I have 6 number of subcarriers and the data rate, peak data rate. I am inventing my own acronym, peak data rate. So if I have 6, I got half megabits. 60, I have 5 megabits. 600, 50 megabits. If I have 1200, that's, I will not go further. Do not worry. I will not be busy for a long time. Okay, 100 megabits per second. So what happened here? If I have 1200 subcarriers, my simple calculation shows me I can support 100 megabits per second. Well, if you have 20 megahertz spectrum, inside the 20 megahertz spectrum bandwidth, you would have the capability of sending out 1200 subcarriers. And that gives us instantaneous peak data rate of 100 megabits per second. But we have been claiming 300 megabits per second. And here I have already exhausted all the subcarriers, all 1200. I am using highest order modulation scheme. So what do I do now? How do I go from 100 megabits per second to 300? Who will show me the trick? Nemo. Excellent. Excellent. Very good. Excellent. Thank you for your answer. So what we will do now, we will rely on multiple input, multiple output. We will use 4x4 MIMO system for the downlink, number of transmit antennas at the base station, number of receive antennas at the UE, and now what we have is one antenna here, another here, and so on. Each antenna is sending out 100 megabits per second. We are reusing the subcarriers from all those antennas. Same subcarriers are being used from all the transmit antennas. The UE also has 4 receive antennas. Okay, and basically we are now getting 100 times 4, 400 megabits per second. Oh, but we do not need 400. We'll be happy with 300. It means then I can take care of some overhead. I can take care of some redundancy that I will introduce through channel coding, turbo coding, for example, and so on. So even after you account for those overhead, redundancy, etc., you will still be able to get 300 megabits. So now you know at a high level how to get the super duper data rate of 300 megabits per second in the downlink. Okay, so this orthogonality, very nice feature. MIMO, yet another contributing factor to high data rate. 20 megahertz bandwidth is also helping, and so is our highest order modulation, 64 pulse. All those factors together help us achieve 300 megabits per second in the down. Now we need to understand one term. If I combine all the modulation symbols on all subcarriers, all modulation symbols on all the subcarriers from a transmitter, I have created OFDM symbol. So there's the definition. One OFDM symbol is nothing but the modulation symbols being carried over subcarriers. In CDMA systems, could be 1X or let's say DO or UMTS, doesn't matter. What goes over the air is chips. How many chips per second? If it is 1X or DO, 1.2288 mega chips per second. If it is UMTS, of course, 3.84 mega chips per second. Chips go over the air in CDMA system. Now, what goes over the air in OFDM system? OFDM symbols. So OFDM symbols go over the air. So the base station transmits OFDM symbols. The UE transmits OFDM symbols. So it is the OFDM symbols that go over the air. So just recapping here, summarizing what we just defined, OFDM symbol is nothing but combination of modulation symbols on all the subcarriers. So we send one OFDM symbol here, another OFDM symbol here, another OFDM symbol here, and so on. So every modulation symbol period, we will send one OFDM symbol because we would combine all the subcarriers using some special techniques which we will discuss later. It is a Fourier transform technique. But that is our definition. Okay, let's move forward. Okay, now subcarriers. We just give an example that okay, if I have 10 megahertz bandwidth, I would have 600 subcarriers. Now, in general, a generic OFDM system will have 4 types of subcarriers. So let's give some numbers here. Okay. One subcarrier, DC, direct current, DC, and that is always at the center of the spectrum, and it is not transmitted. So meaning there is no energy in the center of the spectrum. So it is absent. We do not transmit that. And one use of that is it will help UEs identify center of the spectrum. So let's say you are a UE and you are looking for the center of the spectrum. You are programmed to look at 700 megahertz. But when you power on, you do not have an exact idea of where 700 megahertz is. So you are looking here, you are looking here, yeah? You are looking around 700 megahertz. So around 700 megahertz, wherever you find minimum energy, that's where your center is. Okay. So DC will help you is identify center of the spectrum. Another kind of subcarrier that we have is guard subcarriers. Now, guard also not transmitted. DC not transmitted, guard also not transmitted. Now let's think about this. There is something so-called guard on the left side of the spectrum, on the right edge of the spectrum, and we do not transmit those, no energy. So what do you think? Maybe the use of guard subcarrier. If something is on the left side of your spectrum, right side, and you do not transmit that, how could that help? Again, you can type in your answer through the questions box. Left edge, right edge, not transmitted. Any benefit? Any interference? Very good, very good. Thank you for your answer. Very good. So this will minimize interference to adjacent system or spectrum. The FCC has given us this bandwidth, okay? This bandwidth, let's say 10 megahertz. So we can do whatever we want to do within the 10 megahertz. However, we cannot start using the spectrum that belongs to some other operator or some other system. Okay. So if you have guard subcarriers, then the last active subcarrier would be, let's say, here and here, let's say. And by the time that energy goes outside the spectrum, it has become very, very weak. So then it will not cause much interference to the adjacent system. Same thing will happen to the right hand side. Power going down, going down, going down, and by the time we reach edge of our spectrum, we are observing tiny, tiny power, and then we are able to meet FCC spectral mask requirements. So no need to worry about any penalties from FCC. Okay, very good. So it will help us with the interference with the adjacent system. Very good. So that's another kind of subcarrier. One more subcarrier, so-called pilot. Pilot subcarrier has similar function to the pilots in 3G systems. Let me ask you another question, very simple question. How do we use pilot in 1X, DO or UMTS system? Can you give me a couple of examples of how we use pilot in 1X or DO or UMTS? Use of pilot signal. Looks like you have very long answers, so you must be typing, I hope. Okay, very good. Someone is typing very fast. A lot of answers. Very good. Thank you for your answers. Let me see what you guys said. Acquisition of the carrier. Okay. Measure the signal strength. Okay, very good. It will help the UE acquire the system. Okay. Fear offset. Okay, very good, very good. Okay. So your answers, all of them are valid. All of them are correct. Okay. Same way we will use the pilot here. We will use the pilot during the system acquisition process. Some student mentioned PN offset. So that's how we identify a sector or a cell. In LTE, we will have cell ID, different cell IDs, and the reference signals. Okay, pilot is formally called a reference signal in LTE. Okay. So we will have a reference signal that is specific to a cell. So different cells will have different reference signal, basic. So it's a function of cell ID. Okay. So that's one thing. So during the system acquisition, we can use that knowledge, that information. Also, we will use the pilot signal to measure signals and okay. So that is for handover or handoff measurements. So in 1XDO UMTS, we look at the pilot strength, EC or I naught. In UMTS, we call it EC or N naught. Same way here, the UE will measure the pilot signal strength. And little later, in a future session, we will see that we have so-called RSRP, RSRQ. Those are the pilot strength measurements. Okay. So that will tell us how good the channel conditions are. Okay. And it also gives us a good idea about the channel conditions, channel estimation, and we use that to perform coherent demodulation. Meaning we will look at the pilot signal along with some data to figure out what is on the data channel. So coherent demodulation is another function of pilot. So those are some of the uses of the pilot signal or reference signal in our OFDMA system. So the signal that is sent on the pilot is a function of the cell ID. We use that for pilot measurement, handover measurements, use that for channel estimation so that we can do coherent demodulation and so on. Finally, we have so-called data subcarriers. Okay, so my slide is becoming very busy, but hopefully you can figure out where we are. Data. Okay, here we are data. What do you think may be the use of data subcarrier? And once we are done with this, we will answer your question. Okay. So, data. What do you think may be the use of data subcarrier? Data subcarrier. Okay, that is your traffic. Very good. So we will use the data subcarrier to send our traffic, your user traffic. You can also send signaling messages using the data subcarrier. So very busy, huh? I made the slide busy, but at least we have all the information in one place. Okay, now time for us to answer many questions that we have got. First, let's take up the easy one. Is that on the downlink or uplink? So what we are observing here is downlink, okay, but similar kind of picture would exist. Not identical, but similar would also exist for uplink. But this is the downlink signal for a generic OFDM system, generic. For LTEs, there are some variations. So I mentioned that pilot, we call it reference signal. Okay. And if I have this, okay, now maybe I can clear this up. Okay, so I mentioned that if I have 10 megahertz spectrum, I have 600 subcarriers. So actually, those 600 are here. So guard is outside 600, so no need to worry about that. And these 600, they are actually so-called data subcarriers, but sometimes, depending on uplink, downlink, and some other stuff, sometimes we use the data subcarrier as a pilot. Okay, so some data will become pilot or reference signal, okay, automatically based on the standard itself. Okay. So let's answer some other questions. Good questions have come up. Okay, let's see. Wouldn't you need guard band for all subcarriers? Oh, okay. So the guard. Okay, remember the benefit of OFDMA. Okay, so if I have one subcarrier F1, the very next neighbor F2, another neighbor F3. 1, 2, and 3, they are neighbors, right? So between two subcarriers, no guard band. That is the benefit of OFDM, that you do not need a guard band between two adjacent subcarriers. Okay, there is no guard band. Always remember, no guard band between two adjacent subcarriers because they are all orthogonal. Okay, so as long as you have that spacing 15 kilohertz, okay, so this signal would look like that. Okay, but there is no guard band. So between two adjacent subcarriers in OFDM system, there is no guard band. We have guard band only in traditional multi-carrier system, not in OFDM. Okay, so that's why here no guard. No guard. There is no guard here. We are showing just one line, but actually the signal looks like that. The signal looks like this. So if I go back here, you see the signal, right? It's going. So there is energy. So there is no guard. In fact, there is significant overlap. So if I had guard, it would show up something like that. Let's say here, then here. There would be some frequency range where you would not find any significant energy. Tiny little bit of energy, but not much. So that's the real guard. But we do not have such guard band between two subcarriers in OFDM system. Okay. In fact, there is overlap. You can see a lot of overlap. Again, you can see a lot of overlap, right? Okay. Okay. So let's answer some of the questions. So hopefully that is clear. Guard band only on the left and right edge of the spectrum. Only here, not in between. Okay. Okay. Some confusion that LT would not have guard bands. Oh, yes, that is correct. LT does not have guard bands between adjacent subcarriers. So no guard band here. Between two subcarriers, no guard bands. But only between our system and some other system. So only on the edge. So hopefully that is clear. Okay. So hopefully we answered your question, but just to submit a follow-up question in case there is still some doubt. Okay, so now we have one more question coming. Let's say we have 10 mega spectrum. How many subcarriers? Actually, see, as I mentioned, you can use the 600 number as your actual data subcarriers here. So think of this, the whole thing for LT at least. Okay, maybe I will show you that. Okay, so the 600 number for LT goes from here to here. Okay, so in LT we have 600 subcarriers, and most of them are data. Actually, I'm debating whether I should give. Yeah, maybe I should give that in. Okay, hold on. Okay. Oh, we have time. Okay, good. So let me draw a picture that will make it clear for LTE system. Okay. So let me draw a picture. Now this is for the downlink. Okay. So downlink picture. Now this is LTE. Okay. So I will draw some times here. Here I have subcarrier number. So let's talk about 10 megahertz bandwidth. So I have 600 subcarriers. So I will give some numbers F0, F1, F11, 12, 13, etc. And finally I will reach 599. That will give me total of 600 subcarriers. Okay, now I will draw some this is a half millisecond interval, formally a slot. This is my symbol number 0. This is OFDMA symbol. Symbol number 0, symbol 1, etc. Okay, this is symbol number 4. Okay. So symbol 0 here, symbol 4 here. So this is the first symbol of the slot, and this is the third last symbol of a slot. Okay. For the folks who just want medium degree of details, please have patience with us. Sometimes we have to go into details to answer specific questions. Okay, so this is what will happen. F0 and F0 and F6. And let's say there are okay, F3 and F9. I have a little bit. The real estate problem. Okay, F9. Okay. So, this symbol that you see here, this kind of symbol, that is your reference signal in LTE. Same as so-called pilot. Okay. So this is all data subcarriers. This is all data here, all data here, data. So out of those 600 subcarriers, right, if you pick one sort of block here, I am picking one block of a dozen subcarriers. So inside that block, you will observe that you are using 2 subcarriers out of 12 during symbol 0 and symbol number 4. That is your referencing. So you are not using all the subcarriers, you are using only 2, one here and one here. Similarly, you are using the other 2, one here and one here. So 2 subcarriers out of 12 subcarriers are used for pilot, for your reference signal. But all other subcarriers are your data subcarriers. So as you can see, within that 600, some subcarriers are data and some are pilot, but not all the time. Only 2 symbols out of 7 symbols in a slot are carrying your reference signal, and those are here, symbol number 4, symbol number 0. So hopefully this gives you very, very accurate idea of where the reference signal is. So this is for the downlink. Okay, so hopefully that should clarify. Excellent. Thank you for a question. Okay, okay. So we have 600 subcarriers. Sometimes some subcarriers will act as a pilot or reference signal. And DC, the center subcarrier in the downlink, is not transmitted. So out of 600, right, the center one will not be transmitted. And then one modulation symbol goes over one zeta subcarrier, another modulation symbol will go over another subcarrier, and so on. Okay, let's have a put. What is not correct? What is false? Now, for the second option, faster the symbol rate, the greater the spacing. Okay. So, faster symbol rate meaning we have many OFDM symbols. So, symbol is becoming shorter. OFDM symbol is becoming shorter. So, now what is the relationship between the subcarrier spacing and the symbol time? For option number 2, think about the relationship between the symbol time and the spacing. If symbol time goes down, what happens to the spacing? Does the spacing increase or decrease? So when you're thinking of option 2, think about the mathematical relationship between the symbol time, which is the same as the modulation symbol time. So OFDM symbol time or modulation symbol time, same thing. So if symbol time decreases, what happens to the subcarrier spacing? Think about the relationship. If symbol time goes down, subcarrier spacing, does it decrease or increase? So think along those lines. A very simple mathematical relationship, but hopefully you remember that. And this is very simple, but let me reiterate. Faster the symbol rate, meaning many symbols every second. So your symbol time is now much shorter. So another way to phrase second statement is, if the OFDM symbol time decreases, if the OFDM symbol is becoming shorter, what happens to the spacing? Does the spacing become larger or does it stay the same? Does it increase? Does it increase or does it decrease? If the symbol rate increases, if the symbol time decreases, what happens to the spacing? Okay. I will give you maybe 1 more minute. So you can look at that mathematical relationship so that you can make a wiser selection of your answer. Yeah, for some reason, I always find that this particular question appears a little bit difficult to students, even though I think it is very simple. But for some reason, some students find it difficult. I do not know why, but maybe I need to rephrase my question in some way. Anyway, okay, let's see what we got here. We have 60% correct answer. So, to create orthogonal subcarriers, we do not have Walsh codes. We do not need Walsh codes or OVSF codes. Walsh codes are required for what? 1x. OVSF codes for UMTS, not here. We are not using CDMA. No need for those codes for orthogonality. To create orthogonal subcarriers, we already discussed that during the modulation symbol period, one subcarrier 1 cycle, another subcarrier maybe 2 cycles, and so on. As long as you have integer multiples of cycles, integer multiples of sine waves, then you are okay. Then you have constructed orthogonal structure. You do not need the help of Walsh codes or OVS code for orthogonality in OFDMA. Of course, you need those for CDMA based system, but not here. Okay. Okay. So that is the correct answer. Okay. Now, for some reason, some folks choose number 2. So let's take a look at that. Okay. Very, very simple mathematical relations. So let's go to the journal here. So what is the relationship between the subcarrier spacing and symbol time? Subcarrier spacing is inversely proportional to the subcarrier space, symbol time. So it's exactly 1 divided by symbol time. So modulation symbol period. Okay. So what we are asking in that question is, if we have higher, okay, we say faster symbol rate, so it means that you have many symbols per second. Of course, it means you are decreasing the symbol time. So when you reduce the symbol time, what happens? So if you reduce a number in the denominator, because if you reduce the number in the denominator, what happens to the ratio? The ratio goes up. So if the symbol time goes down, what happens to the subcarrier spacing? It goes up. So it becomes larger. So if you have faster symbol rate, your subcarrier spacing would become larger. So in a generic OFDM system, okay, if you have faster symbol rate, then effectively larger spacing. In LTE, you never touch the symbol rate. So your symbol time is always fixed at 66 micro. You never touch the symbol rate. The symbol time is always fixed. If the symbol time is always fixed, right, then you will always get 15 kilos. That is LTE. But in the question, we are saying that if we have a faster symbol rate, so if symbol time goes down, then what will happen? Okay, so that's why we had asked the question in that way. But yeah, maybe I should just refrain from using the generic non-LTE type approach. But you cannot choose that option number 2 because it is correct. It's not false. It is true. And the first statement is of course true. That is the definition. OFDM symbol is nothing but the modulation symbols on subcarrier. So the last option number 3 is not correct. Okay, so looks like some okay, mathematically a faster symbol rate means a greater spacing. Okay, okay, but faster fewer subcarriers. Oh yeah, that is correct. That is correct. So if you have larger spacing between subcarriers, then you are right. Of course, then we will have fewer subcarriers in the available spectrum bandwidth. Absolutely correct. Okay, then we have one more question. Oh, some of us chose number 2 because subcarrier spacing. Oh, I see. Now, maybe that's why some of you choose number 2, because I emphasize that in LTE, we never touch subcarrier spacing, right? It is always fixed. So maybe you are thinking from that perspective. That's why some of you choose this. Now I realize why I have lower performance rating on this question. Maybe, yeah, I should keep this LT specific, and that will help us with the performance numbers here. Okay, yeah, maybe that's the reason. But if the symbol rate is faster, then of course the spacing would be greater. Okay, so we cannot say that it is false. It is a true statement. Okay, we have one sort of question. Okay, or comment rather. Oh, fewer subcarriers means less throughput. Oh, now not necessarily. See, you are basically having this two-dimensional resource grid. So one dimension is your number of subcarriers, another dimension is number of symbols. So if you have shorter symbols, right, then you have basically more symbols. Right? Fewer subcarriers but more symbols. So if you have certain a time period, you can send many OFDM symbols, even though you may have fewer subcarriers. So we cannot say that it's always less throughput. So it depends on the channel conditions and lot of other factors, whether you will have slightly better throughput or slightly lower throughput. But if you have more subcarriers, then you have shorter, more subcarriers. Yeah, so lower spacing, narrower spacing, meaning more time for the symbols. Yeah, so it's just a trade-off. But you have two-dimensional grid. Either you have more symbols or you have more subcarriers. Okay, one of the two you will have at a given time. Okay. Okay. Let's have a short break, and once we come back, we will have audio bridge unmuted, so we can discuss some issues at that time. Okay. Okay. So 10-minute break starting now. So we'll come back in 10 minutes. The news